Okay, so now we'll look at transforming functions that involve the unit step. We go back to the definition. The transform is the integral from 0 to infinity of e to the negative st times our unit step. But what's really interesting about it is our unit step function is binary. It's 0 or 1, which means that this integral is either transforming 0, which goes to 0, or transforming 1, but only over part of the interval. So let's first break this up. To integrate from t equals 0 up to c, and here you get e to the negative st times 0 dt. And then if you integrate from t equals c to infinity, you have e to the negative st dt. Oh, times 1, sorry. There you go. E to the negative st dt, right, times that 1. And so we ignore the portion that is turned off. We could just integrate out. This is an exponential, integrate really nicely. But I want, it's so close to a Laplace transform, I just want to rewrite the equation using a new variable. So I'm making a u substitution in a sense for the t variable, replacing it with a tau. I'm not using a u because, well, unit step, I guess that's a little conflict of interest here. So a u substitution with a tau, there we go. So it gives me an integral with new limits. Since I'm integrating from tau equals t minus c, I simply subtract c from the limits. So tau goes from 0 up to infinity minus c. That's still infinity. And then we have e to the negative s times, well, what does t equal to? Well, tau is equal to t minus c, so t is equal to tau plus c. There we go. And then d tau. Well, let's simplify this out a little bit. I have an e to the negative s tau, that makes sense, but it's also a minus sc, which is constant in terms of tau. So if we factor that out, e to the negative sc or cs, what we have left is the integral from tau equals 0 to infinity of e to the negative s tau d tau. And now what we can have is the Laplace transform of the unit step pulls out an exponential, but in the frequency domain, and then multiplied by the transform of 1. Since tau is dummy variable, we could think of it as a t here. We're just transforming the function 1. And that is 1 over s. So we have e to the negative cs over s. Now, there's an interesting relationship. Whenever we transform a unit step function, we need to think about what it's multiplying by. And in this case, it's multiplied by 1. We're switching on a constant. And because we're switching on a constant, we get the activation of that switch when it occurs at t equals c. And then what the function is that's being switched on. In our case, it's a 1 over, in our case, it's a constant, so it's transformed as a 1 over s. Oh, I'll leave that. So So I guess I could say this is a 1 times unit step function is the e to the negative cs times the transform of 1. In the same way, we'll see that if we transform any function of t times a unit step, we'll get out e to the negative cs times the transform of that function. But the only caveat is that this function has to be shifted in time to match our activation. And if it's shifted in time correctly, then we can factor out the activation, e to the negative cs, that tells us that there's a unit step activation happening at t equals c, and then the transform of that unshifted function. Okay, so now we're going to go through the same process to prove our second property, that if you transform any function, as long as it's shifted correctly, you can get the same activation in the frequency space, e to the negative cs, times the transform of the unshifted function. Let's see. We're integrating from 0 to infinity, e to the negative st times our f of t minus c times u of t minus c. So first, we know this is a binary function, so it means that we're 0 for all values of c of t less than c. And then we're integrating from t equals c on up to infinity of e to the negative st times f of t minus c dt. And again, this is so close to a transform that we want to rewrite it using a u substitution, or in our case, a tau substitution. Changes our limits from tau equals 0 on up to infinity. We get our e to the negative s tau plus c again. And now that t minus c turns into an f of tau. So the function gets shifted back just like we expected it to be. And then we factor out e to the negative cs, and we have the integral tau equals 0 to infinity, e to the negative s tau f of tau d tau, and here we have the transform of our function, or in another way, e to the negative cs times the transform of f of t, which for shorthand we have e to the negative cs times capital F of s. Whew.